All right, I wanted to talk about several things today, and I thought perhaps a good introduction would be to review a topic I brought up a couple of years ago. We have people who work on hardware and people who work on software, and one of the things that we had often come up was that some of the hardware designers would say, well, we need to put this feature into the hardware because of software. And we'd say, well, but we don't think of that in software. And the one that came up today, I heard several times, was lockup. You're going to get lockup. Your programs are going to lock up. They're going to lock up on you. And we heard this over and over from hardware designers. It's absolutely true. The software people are going to lock it up. We don't know how to write software, so we're going to lock up the machine. And we need hardware to unlock it. Well, our design is pretty much a minimal design where we don't like to put in a lot of extra hardware to do things that we can do in software. And our thought was that we're writing these programs, we should be able to write them without locking them up. So we would often just sort of say, well, we'll try to teach you how to write programs.
Good luck with that.
Yeah. And what I have found with that is that this is sort of a universal problem with parallel programming, it seems, is that most people have experience with sequential programming. They're moving into a world now where everybody's offering multi-cores and they're dealing with the internet and applications distributed across many locations and running in parallel. And they're concerned with how to not lock up their applications because they don't know how to do it. In fact, it goes back to structured design and analysis. Back in the days when I worked at Bank of America, we took courses on designing and implementing programs. And one of them was we studied was the Jordan methodologies. You may have studied these yourself. How to break your project down into little pieces, diagram what each piece does. Well, this formal approach has been expanded since those days, and we're using this type of approach in Forth, at least some of us are, and find it very helpful in solving that problem of how do we deal with this lockup issue. So again, let me just give you a little review. Our design has a hardware implementation of Forth. What you used to think of as much of Forth is gone. It's moved into the hardware. We don't have to implement dupe as a string of opcodes, and we don't have to implement drop and over and all of these things that you have to implement in a virtual machine in a normal Forth system. Those are our opcodes. And this hardware Forth is particularly compressed because these opcodes are no longer entire words. They're little 5-bit opcodes that we pack multiple opcodes into a word. So our Forth programs become even more dense than normal Forth programs, and they become faster than normal Forth programs because we're executing our primitives at the hardware level. We also have hardware to assist in parallel programming. Our communication ports between the machines implement a software construct known as a communication channel. You have a program running, it sends a message to another program, that program says, oh, there's something to do, it wakes up, it reads the message, it decides what that message tells it to do, it goes and does something, and maybe it goes back to sleep waiting for another message, or maybe it sends a message out to somebody else. Back in 1967, C.A.R. Hoare introduced a concept called communicating sequential processes. And it is exactly this notion, but extended to the world of parallelism. Now you can have multiple things running in parallel, and instead of multitasking where only one of them is awake at one time, you can have lots of things wake up and run in parallel and go to sleep when they need to and wake up when they need to. And normally you have to implement this as a software layer, unless you're dealing with something like the Transputer, which was a hardware implementation of the Occam language and the CSP, and it had hardware communication ports that, like ours, let one processor go to sleep until the other processor that it's talking to responds. And just as our instruction set simplifies Forth, this these communication links simplify the parallel programming because they allow you to use the Occam type communication, the communicating sequential process model, which other people are using in other environments, but to use it in Forth. And all you have to do is write something to a communication port, and if the neighbor hasn't gone to sleep reading, you go to sleep until the neighbor reads it. Or you read a communication port, and if the neighbor hasn't gone to sleep writing it, you go to sleep until the neighbor writes it. And as a result, the communication is just a matter of writing to a port, and the coordination between processes is just done automatically on this data flow. So if you structure your application now as small modules based on their data flow, this is going to represent the flow of data throughout your application, something that's done in structured programming, but something that corresponds very closely to what's called event partitioning. In event partitioning, you take a complex application and you break it up into small pieces. Each piece should be simple, easy to understand, and it should have simple inputs and outputs. Some event happens, you do something, you send a message. An event happens, you get a message, you process it, you send out another message. And this is the approach that we're using to deal with the parallel aspect of more complicated programs. Now, if you're dealing with really simple things, and I'm going to show a couple of very simple applications where the data flow is pretty trivial. It starts here, goes to that node, the next node reads here and writes there, and the next node reads here and writes there, and the data just passes through a stream. Sometimes the data flow can get more complicated, and what I have done as a habit now is to put a data flow diagram as a comment at the beginning of each word. Just as we have a diagram showing you the stack effect of that word, we use a diagram to show you the data flow. For instance, I use the character O to represent reading or writing the output port. A capital O means write to a port, and a lowercase o would mean read from the output port. And I have a little notation that we use for describing the data flow from one module to another. And the advantages of this are numerous. One of them is that if you do have a lockup, you know right where to look. You've probably made some change to the data flow somewhere that's no longer balanced. But more importantly, while you're designing your program, you can actually first design it around its data flow, write your diagrams for how the data flow is going to work, and then generate code templates from that data flow. And I'd like to show you an example of doing that. Oops, that's this one. Here you can see an example where I have a data flow. Read from the input port, write to the output port. Okay? So I've described a very simple module. That, assuming that we then assign the A register to point to the input port and the B register to point to the output port, this diagram translates directly into some code. Fetch from where A is pointing and store to where B is pointing. Read the input port, write to the output port. So we can take a data flow diagram of a module, translate it into opcodes, and generate test cases. Here is this means repeat. Begin, fetch from A, store to B, and do it again. Now there's no processing going on here, but what this does is this gives me something that if I drop this on a node now, it's going to implement this data flow. And I can set up my entire application this way and set up its data flow. Now I can run it and there'll be no processing going on anywhere, but the data that I believe is going to flow in a certain way is going to flow that way, and I'm going to be able to debug it. It's very simple, very straightforward. And I can at any time take the modules that I develop and replace them with my original data flow modules for debugging purposes. They act as test case implementations for debugging, as well as a template for getting your code started. Okay, so that looks pretty straightforward and simple. But sometimes you want to treat a group of nodes as a module. And we just refer to this as a group. So you implement this, and then originally when testing it, you can put it on one node, and it does the data flow for some group. Data comes in, the group does something with it, data goes out. Now you debug your application. After you've done that, you can take that node, and you can say, okay, now I think I'll put 8 nodes inside of that group. And inside of that group, there's going to be some data flow going on between the members of that group. So I can take my original diagram and expand it with a little algebra, saying the group number, the node number, if this and that. Generally, the way these things work is that the first member of a group and the last member of a group are a little bit different, because everybody in the middle of the group is going to pretty much be doing the same thing, except for being in a different position. The guy at the beginning is probably not doing a dupe, and the guy at the end is probably sending a result out. So there's going to be a little difference on the first guy and the last guy, and then everybody else in the group is going to do the same thing based on his number. In this case, I'm using M for elements and N for nodes in a group. One of the applications we did last year were some image processing applications for BMW. I found the experience quite amazing. When BMW first came in and talked to us about what they were doing, I was quite amazed. They said, when we first sold cars, they had 40 meters of wiring in them. Today, our cars have 40 kilometers of wiring in them. Yeah. They have 40 kilometers of wiring, 600 motors, 100 processors, 20 networks. I mean, this went on, and I'm like, you're talking about a spacecraft or a car, you know? Okay, well, one of the things that they're doing is that they have video cameras that are scanning and looking for pedestrians in the crosswalk in front of your car. So when the light changes, if you stomp on the gas pedal, the car will resist your intention to run down pedestrians. Okay, now, yeah. So this was one of the applications that we looked at, and the suite involved a number of graphics image processing applications. One of them, the last one I worked on, was the disparity map, and the disparity map actually is taking 2 different images from 2 different cameras and doing a disparity to figure the distance away of the pedestrian. So first they have to figure out there's a pedestrian in the image, then they got to figure out the difference between 2 different images and all. And the way this thing worked is it takes pixels from the video image and it brings them in and processes them in a certain way. When the intern originally designed it, the idea was you have to break up a line of video or several lines and bring in the pixels and process them. So what she was doing was to just do it in a very straightforward way. Let's assign 18 pixels to 9 processors and let them perform this algorithm. In fact, let's have 4 groups of 9 processors in each group, which will receive 18 pixels and process them, and then we ship them out. So we set up this sort of pipeline, and in the original implementation, one end is bringing in the pixels from the image in a certain way, passing them to groups. The groups were originally implemented as just one node reading pixels and writing pixels, and then was expanded into a group of 9 nodes, with each one of its members doing something slightly differently. And I looked at it and said, well, we're sending 18 pixels, and then we're moving to the right 1 pixel, and then we're sending 18 more pixels, but 15 of those pixels are pixels that we sent last time. And that seems pretty wasteful, because they're already sitting there in the computational memory of nodes that got them on the last set. So I said what we should do is reduce the pixel traffic, which was our bottleneck, by a factor of 6. We send out 18 pixels, and then from that point on, we just send out 3 pixels just after the group has rearranged its pixels in preparation for getting 3 more. So each time we just send out 3 more, and now it's got a new group of 18 pixels to work on, and then we send out 3 more, and each group has a new arrangement of 18 pixels to work on, and it sends its results down to the end where things get collected and get turned back into a video image. One of the things I found interesting on that was at the very end I was writing the code for the node at the end, and I needed to get the parameter for where the y is in the image. And my first instinct was, oh, I'm going to have to send that all the way from this node through all of the processing nodes to the node on the end. And then I said to myself, oh, wait a minute. I've got data flow here. These things are all in lockstep. My node at the end has exactly the same loop structure as my node at the beginning. That was the first thing I debugged in the data flow, was to have the node that reads the data from the video image and send it just through some other nodes to the node that's processing it, and they have to stay locked step. So all I have to do on that node is look at the index on the return stack, and it's my y value, because it is synced with the beginning node. More importantly, the stack diagrams got pretty complicated because we're dealing with 9 members of each group, 4 groups in the pixel processing. They're receiving pixels, processing them, sending them out, and then exchanging them with their neighbors in the middle of this process. And it was easier to debug by using these sorts of data flow diagrams. Now, here's an example of a diagram that that says the number of nodes and the number of members times each other. We're going to do input and output that many times, and then we're going to do input according to the number of members. And then if this is not the last node, we're going to read from the output port, and then finally we're going to write to the input port. And this sort of description lends itself to several things. One of them is you can verify that the neighbor, that a neighbor's data flow is not going to lock up with its neighbor. As long as their data flow diagrams are complementary, everything is fine. The only time you'll ever have problems is when you've got data flow diagrams that don't match. If you've got one node that's writing 3 times and then reading, and his neighbor is reading twice and then writing, it's not going to work. They have to have complementary data flow diagrams. So having this sort of notation at the beginning of each of your modules lets you look at one module and say, okay, I can drop this module next to that module, and their data flow is going to mesh. And you can prove mathematically that your data flow isn't going to lock up. You can generate your test cases. You can use your test cases to then implement actual code. Okay, here was an example of a data flow diagram statement, and here is code generated to match that statement. Now you'll notice we're using these left brackets, which are because we're switching from compiling for our machine to doing ANSI forth. So this is normal forth here. N times N, bracket if, then generate a number, and do this if this is not 0. And again, these are the special cases for the beginning and end nodes. And here is the port pump. In this case, we're just reading in our loop. And then at the end, we're writing one result out, and then we're looping back. So again, this diagram translates into that particular statement. And you can apply some algebra simplification to some of your diagrams before you translate them. I experimented with doing this translation automatically with the software. I didn't follow through on it because I kept making changes to the notation while I was developing the software, and I said, hey, I shouldn't be working on a moving spec like this. I should just translate these by hand. But it was very helpful in doing the work we were doing, and it does lend itself to machine translation for generating these diagrams. More importantly, it lets us classify these library modules by their data flow. So that if you want a wire, you can look at all the wires and look at the data flow. The simplest wire is probably that thing I showed you. Input from one side, output to the other side. Simple unidirectional wire, copies from one port to the other port. I have one example today I'm going to talk about, which is the talking voltmeter example. Very simple application. But in one of the implementations, the data flow was complicated a bit by the fact that SPI was down in a corner, and I had the commands going to the SPI player on the same wire as the data coming back from the SPI player. So the data flow looks something like from SPI, read from the output port, write to the output port, write 64 values to the output port, and repeat. And so what it's doing is it's synchronizing with the thing that's requesting. It's looking up stuff on the SPI and sending it 64 words at a time back down the path along with a counter. So the node down the down path knows how many more sound packets are coming, and after the last sound packet has come, it's now ready to send real commands back down the other direction down this pipe in order to get a response from the SPI player. This final example here shows you that once you have defined your data flow on a node, you can go into your library and compile your code. And you can drop your code right into your template, and you've now generated the application for that node. The way that this separates debugging, designing and debugging your data flow from the traditional sequential programming that you already have mastered is there to solve that problem that people have, which is that they really don't know how to deal with that data flow problem yet and how to avoid getting into these situations where their programs are going to lock up. So let me go back to this one and show you a little more of an example. One of the things that I was working on was some analog applications where we're going to use the A to Ds and D to As, and we needed to characterize them. Now, our philosophy is that the hardware is simple and that we use software. So our A to D and D to A are not perfectly linear. 10 more? Okay. Our A to Ds and D to As are not perfectly linear, and we assume that we use software to linearize them. So I set out to do this both at audio speed and at video speed in a couple different applications. In the case of analog, I set up an A to D node that's sampling at a given rate. The rate could be determined by the outside world, could be determined by another node. In this case, it's just being determined by internal timing. So that node is sampling the analog to digital converter. And the way our A to D works is that we have a voltage-controlled oscillator, and the voltage on the input will be proportional to the rate of oscillations. So you take multiple samples and you subtract, and you get a count, which tells you how fast that voltage-controlled oscillator is going, and it will follow the voltage on the pin. Now, to linearize it, I said, okay, well, a simple way to do that would be to have a data table with 64 values in it and read 2 of them and interpolate between them. So I just took a neighbor and put a table on it. Now that node, and that neighbor has no code. what it's doing is, after it's loaded its table into RAM, it jumps to the port adjacent to the node with the A to D. So it's trying to execute the port connected to the node that's doing the digitizing. When that node gets a value from, actually it's talking to the linearizer node. I split these. So sample node gets a sample and hands it to the linearizer node. The linearizer node sends a message to the neighbor that's reading its port that has nothing but data in it to take this value, use it as an index, look it up in your memory, and send it back to me. The code is literal, A store, fetch from A, store P plus, store back to the program counter of the port that I'm in. So I'm executing a port. I send an opcode and data to the port, and that opcode and data reads from the memory of that processor and then writes back to the port that I wrote to, which I now read the data back. So that gives me a nice linearized version of the data that I've read from my analog processor. Now, I intended to do other things with it, but in the process of debugging this, I thought, well, I've got a number of ways to instrument this. I can send this information over here. I can send it out with pulse width modulation. I can send it out as an analog value. I can send it out as a digital number. Well, I can send it out as a sound on a pin. Why not? It's a trivial thing to do. I looked in a example of programming microprocessors and saw this was one of the simple, trivial examples they use to train people is write pulse width modulation and write an SPI driver. And so what I did was, we have a node that boots up in SPI. It is connected to an SPI flash. It has ROM code to boot packets from that SPI. So I put some code in that node's RAM to call some of that code to read data packets from the SPI flash and send them out. Very simple thing. Now, I put a couple of nodes upstream. And these things are just doing trivial things. One of them takes the number sent to it now that's been linearized from the A to D, and it breaks it down into 5 digits. 6 digits? And 6 decimal digits. Then it sends those 6 decimal digits to the next node. And that node has a table where it has a table of 50 values where an index into its table will return an SPI address and an SPI length. So I put originally 16 hex numbers in there. And my index was 0 to F. And if you sent 0 to F to this node, it would look up in its table and it would tell you the address that I had put the recorded sound for 1 or 2 or 3 in the SPI and the length of that routine. And it would play it. So, we've got these nodes, and we now have the SPI playing these sounds. They come out, they go to a splitter. The splitter is there so that we can feed this data buffered to the output, and there'll be a little bit of time where we can go off and send another command back to the SPI player, and it can go through its process, and it can load more sound data, and it can send it all before the sound we're playing now is done playing. And I did that very simply by having a node that it's got a stream of 64 words coming in at a time, and it is on a diagonal to the node that's playing the sound. And it writes to one of its 2 neighbors. It writes 64 words to the right, and then it writes 64 words down, and then it writes 64 words to the right, and then it writes 64 words down. And the node that's playing the sound is the other diagonal, and it reads 64 words from here, and then it reads 64 words from there, and it handshakes. There's one more word used for handshaking. So that final node that's playing the sound can either be a D to A, in which case we just take the sound packets and throw them right to the analog port, or it can do PWM on any of the GPIO digital pins on a digital node at audio speed and produce the analog signal on the pin appropriate to the value in the sound file. So a description of the talking voltmeter is that when it begins, a boot packet will load, and this will either be sent in from off-chip for debugging purposes from my PC directly, and then run, or it gets loaded in Flash so that when you reset the device, the whole thing comes out of Flash. Now, when I was developing it, I put parts of it in Flash. First thing I put in Flash was the sounds, and then I put the player, and then I put the digitizer and the speed and those modules, so that that whole group became known as Speak Decimal Number, and that was now in Flash. So you boot up the chip, out of Flash comes Speak Decimal Number, and loads on a bunch of nodes. Now I just load my little test program on some other nodes, and it talks to the Speak Decimal Number group, and the sound comes out on the speaker. To flash the whole thing, I load the whole application. The compiler compiles it as one packet, such that that packet can be put into the SPI and will come out of the SPI when it's booted. We'll distribute my program to each of the nodes where it resides and launch it. And again, I don't need to know the details of how that works. All I need to know is that that's what the compiler does when I click the icon that says I want to compile my application and put it in Flash. And the compiler builds the packet, sends it, loads it to the Flash, and now if I hit reset, the thing comes out of Flash. So again, the way that this is set up depends on the implementation, but on the S40, it's very straightforward. We can have node 36 read from its A to D. Node 35 is a linearizer with a table on 25. It sends output to 34. 34 splits digits, sends its output to 33, which converts the digits into an address and a length to be played on SPI, hands it to the SPI player, which plays the sound from that, hands it to the splitter, which then puts it into one of two buffers. It comes out of those buffers, goes to a pin, and you get the sound. So to calibrate this, I put a potentiometer on there, and you twist the potentiometer, and you get a 6-digit value on the digital voltmeter in the lab, and the little device speaks the voltage out down to accuracy of within a millivolt over the whole range of this device. It's nice. It runs on either S40 or S24. It only takes a few nodes to do it. It's very simple and trivial. It's slow, so the thing's asleep a lot of the time. And it's an example of a simple application with simple data flow. Here's a picture of it laid out on S40. This node is just taking samples and subtracting and getting a difference, giving the difference to this node, which looks it up in a table and linearizes it. This node splits out digits. This node turns the digits into the appropriate address and length of the data in SPI. The SPI plays it using these 4 pins talking to an SPI chip. It comes out of there, and it goes into one of these 2 buffers. It comes out of the buffer, and it goes to this node, which pulse width modulates it, and it goes out on a pin. And if you put a speaker or an earphone on that pin and twist the potentiometer on the A to D, you hear it speaking out the voltage on the device. So it's similar to I2C, but a little less complicated. It's a simple device. Yeah. I2C has more command variations. And and SPI, the important thing about it is that the processor generates the clock, which can be anything from DC up to the maximum speed that the parts run at, which is today is about 55 megahertz. So they're very, very simple, very cheap devices, and that's what we're using for our flash interface. Yes?
Are we going to get a demo?
I have a demo set up over there. I don't currently have the speaker attached to it, and I can't let everyone hear at once, but we've got that. Another one I wanted to talk about. How?
A minute or two?
One or 2 minutes.
Michael for his half hour.
Okay.
Quick question.
Yes.
I mean, it speaks. I mean, could you be able to put like someone else's voice in the thing?
Oh yeah. Well, one of the reasons for 50 sounds in there is that you can do phonemes, for instance, or all the sounds in Japanese or whatever. But
Put like Dick Nixon's voice or Truman Capote's voice.
oh, sure, sure. I'm just playing sounds. It's just a table that's playing sounds from the SPI player. Now, I have another demo that I set up for video. One of the things we did with the Sobel demo for BMW is we're processing these video images. So we took an NTSC camera, cheap one, threw it onto our chip, and ran it into the A to D. Do the same thing with it. Read it real fast, linearize the result, do something with the result. So what I did was I generate a video output based on the video input while looking at the video frame and finding the pixels so that we can pull the pixels out and process them and do something to them. And basically this is very simple. We've got an A to D node reading data in. We've got a linearizer and a table, the same setup that you see here, except we're pulling that out, and then I have one node doing something to it, and then I'm sending it back out as an analog signal. And you can see if we hook up a monitor that we're outputting low resolution analog video live from the camera, going from analog to digital and back to analog, and at the same time analyzing the frame so we can do something with them, like pull the data out, massage it, do image processing on it, and insert it back into the frame with some kind of processing being done. Edge detection or motion detection or whatever we want to do. So those were the things I wanted to talk about today. I think my time is up, but if there's any more questions.
The story is just good for chat. It integrate very complicated. If you perfectly integrate 20,000 systems, right? AI in the drive for low power integrate text velocity and a simple integrate not too linear. And it was so proud they put a hardware linearizer, which is a state machine, make it linear. So they said, wow, look at our wonderful invention. The difference is our linearizer in the software is flexible, can be calibrated. The hardware, you did it once, calibrate once. If the manufacturing changes, you don't change your linearizer.
And I will say on the video application, I have one table, which is a table of voltage count from the VCO into voltage out for the D to A. And it takes care of linearizing both the input and the output at the same time. So that we bring it in from a nonlinear device, put it through this table, bring it out, send it to a nonlinear device, but it turns linear in the process. And you can calibrate that table. For instance, if you want a negative image, if you write the table inverted, the output image suddenly becomes inverted, and that's all you have to do to it. And I did a couple other little tricks to using the table that way. For instance, I cleaned up the sync and blank signals because our sampler samples over a window, and because that window is variable, and because we had it set for a pixel length, it was possible for you to sample while going from blank through a black pixel, and you'd get these positions that were not clearly defined as either sync or blank, but sort of halfway in between them. And all I did in my output table was to have all of those values either be sync or blank, and it comes out cleanly sync or blank if it's below this level. Otherwise, you get a pixel level. And it makes a nice clean video output frame on the output. and it allows for trivial processing. And again, it's using this simple technique for A to D, D to A, and a linearizing in software. Uh-huh.
One more question. Regarding the A to D to linearizer transition, I noticed that in C424's documentation, they recommend that you XOR the ADC reading with 155 hex. If you calibrate the linearizer table, do you still need to do that in order for the benefit of the subtraction?
Yeah, the original, the S24, it worked one way, and we made some changes to it, moving in one case from hardware to software, in the other case from software to hardware, so it would work better. And now you're required to do that in software. So one part of the process is you have to turn it from a pattern with inverted bits into an ordinary number before you do all this operation on it. But it's an exclusive OR.
Yeah, but I guess what I'm saying though is it possible to do arithmetic on the actual patterns and then calibrate the linearization table based on patterns?
You wouldn't want to try. I wouldn't say it's not impossible, but it's not worth the effort. It's insanely weird to try to work on those patterns. You just turn them into a number and they're normal things.
Okay.